Polyprotic acids are an interesting topic. First, notice poly. Basically, we're talking about acids that have more than one proton, okay? So poly means more than one. Protic, talking about a proton, so we're talking about acids that have more than one hydrogen ion that they can donate. So in all these examples, notice that below the hydrogen ion there is a subscript 2 or 3. Okay, so they have more than one hydrogen they can give up when dissolved in aqueous solution. They always dissociate stepwise, so the H's come off one at a time. The first H always comes off the easiest, and then the second, and then the third. This means that the Ka for the first step is going to be much larger than the Ka for the second step, and then so on for the third step. These steps are going to be denoted Ka1, Ka2, Ka3, so that's how you'll know what step it's associated with. When we say step-by-step ionization or dissociation, we're talking about one hydrogen coming off at a time. So first you would have, for hydrogen phosphate, H3PO4, the first hydrogen would come off and you'd make H2PO4. Then that H2PO4 further can dissociate into H plus and HPO4 2 minus. That H2 minus, HPO4 2 minus can then dissociate one more hydrogen and become PO4 3 minus. So altogether, you're losing 3 total hydrogens, but they come off one at a time. All right, in this example, we have hydrogen carbonate, H2CO3, and you see that it has 2 different Ka values. The Ka for the first step is larger than the Ka for the second step. And when this HCO3 minus is over here, it's considered a base. It's considered the conjugate base of this acid, but then in the next step, again, it becomes an acid and then can form another conjugate base. We usually don't have to worry about the second and third dissociations, and you'll see why in a minute when we do some calculations. They don't affect any of the other concentrations very much. The first hydrogen always comes off much easier than the second or third hydrogens. That's always something good to keep in mind. All right, so let's look at a practice problem. So here we have H3ASO4, which is arsenic acid, and it's a 1 molar concentration. Then we have 3 different Ka values, 1, 2, and 3 for each of the hydrogens that comes off. Okay, and it wants us to calculate the pH. Okay, so these are so much smaller than the original that we really only need to look at Ka1. So we're just going to scratch out Ka2 and Ka3 because they're not going to be very important. So we got H3, ASO4, and that is going to dissociate. My son, he's running around. H plus, and then you'll have H2, ASO4 minus. All right, so we started with 1 mole of this, or 1 molar, so mole per liter, and we had 0 of these. Minus X, plus X, plus X, and at equilibrium we get 1 minus X, X, and X. So that completes our ice table. Now we just need to plug this in to our expression for K. So X times X on top, so the products are X squared. And then on bottom, 1 minus X, and that's equal to the K value of 5 times 10 to the negative third. So we can cross this out because this is much smaller. And we get X squared is equal to 5 times 10 to the negative third, which gives us, all right, and that's going to give us an X value equal to 7.07 times 10 to the negative second. All right, so that is our H plus concentration. So now we can negative log that, and that will give us the pH. So we're going to negative log the 7.0 times 10 to the negative second, and that gives us a pH value of, so the pH is 1.15. Okay? All right, now sulfuric acid is a special polyprotic acid because in the first step, it's a strong acid. The second step has a Ka of 1.2 times 10 to the negative second. So when you're looking at these, you're going to have to first talk about the first step and then look at the second step. So if you were to calculate all the concentrations in a 2 molar solution of H2SO4, first you'd have the H2SO4, and this is the first hydrogen it's losing. So it's going to be a strong step. So that means that if we started with 2 molar of the acid, that it would form 2 molar of the hydrogen ion and 2 molar of the hydrogen sulfate ion here. Okay. All right. Now, that's the first step. Now we need to look at the second step. So in the second step, the HSO4 minus is going to lose the last hydrogen to become SO4 2 minus. Now we need to look at an ice chart to try to determine all of the concentrations at equilibrium. And we know that our original HSO4 is 2 and our original H is 2. Okay, and we have no SO4 2 minus at this point. So we're going to minus X, plus X, plus X, 2 minus X, 2 plus X, and X. So we get this in our equilibrium expression. We have X times 2 plus X, so this is products over reactants, and then 2 minus X. That's equal to the 1.2 times 10 to the negative second Ka. All right, so it's a small Ka, so we can cross out the pluses and minuses, which also gets rid of that. So this is our X. So that means that we have 1.2 times 10 to the negative second of the HSO4. And then we have 2 plus that, so 2.012 of the H plus. And then 2 minus that, so 1.988 of the HSO4 minus. Okay? All right, let's look at one more. All right, so which of the following are polyprotic acids? All right, a second to think about it. Hopefully you said C and E. So you see the H's in the front. All right, NH3 is a base, so that's not a good choice. This one, only this H can be removed. And strong acid, but they only have one proton. All right, sorry about that. We had a little small crisis over here. All right, so now let's look at which acid is harder to ionize. So you got H3PO4 or HPO4 2 minus. Okay, and why? Well, hopefully you said that HPO4 2 minus is harder because it's charged, number one, and it's already lost some some protons, some H pluses, okay? And because it has that charge, it's attracting H pluses towards itself. So it gets harder and harder to remove them once you take the first one off. So the first hydrogen comes off easiest, and then it gets harder and harder. Which acid is stronger, H2SO4 or HSO4 minus? And why? Well, you know that H2SO4 is a strong acid in the first step, and you also know that it's easiest to lose that first proton. So after you lose it, it gets harder, so that becomes a weaker acid.